Hello guys, hello guys. Yeah, it's our day, guys. Grade 12, how are you? How are you guys? I hope you are practicing now. Hello guys. Today it's our days. I'm here to help you guys, grade 12, for you who are practicing for their final examination. So now we are no, our technical issues solving, guys. Let me hit our screen here on this side. Yes. Okay. Hey guys, hello guys. Today is our day. I'm here for you guys. I'm here for you. Hey, here we go, guys. Today, our business is to do physical science, chemical, paper 2. We are doing chemical equilibrium on question 6. We'll do it. Question 6 is a chemical equilibrium which is consist of 15 marks and above. So on 6.1 it reads as follows, guys. The following reversible reaction can be used to demonstrate how a certain factor influences a chemical equilibrium. So here's our balance equation that we are given. So our 6.1.1, they ask us to define the reversible. Something that is reversible is something that it can change from one step, or like it's like a car. A car is a reversible object. It can go forward, but it can also go back. You see, so now here we are on reactions now, guys. This is when the product can be converted back to its reactant. So I will not go much. I will not waste time by defining or by writing the definition, but I will just repeat it. Irreversible reaction, guys, it is when the product can be converted back to its reactant. So guys, to save our time, let's go to 6.1. 6.1.1, it's a definition. It's on your notes, guys. Define reversible reaction 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 reaction. So go and check up your notes, guys. 6.1.2. Okay, here on 6.1.2 are given the scenario. In this scenario, they say initially the solution is blue. The solution is blue. Write down either the solution, it will turns more blue or turns more pink. To describe what happened to the mixture, to the reaction mixture, if some tetrachlorocobaltate ions is being added, that Cl4 2 minus is chlorocobaltate ions, guys. So if we're adding chlorocobaltate ions, we are changing the solution to become blue. if it's react with hydrochloric acid. You see, so now what will happen if we are adding COCl 2 minus on the reactant, which means now when we are adding chlorocobaltate ions, we are adding the concentration of our reactant. So when we are adding the concentration on the reactant, which means the forward reaction, it will reverse in order to balance the chemical reaction. Remember guys, the substance for chemical equilibrium to happen, the substance must not be equal, but the forward and reverse reaction must be equal. So if you decrease the number of moles on the reactant, you are also allowing for sorry guys, how our stream is gone already. Let me try to reback it. Our stream giving us a problem. Sorry guys for our technical issues, but I will try by all means guys. I'm sorry. I was saying that if you are increasing the concentration of our reactant, it's whereby you are allowing or you are favoring the forward reaction in order to increase the product, or the number of product that will be produced on the product, which means now the reaction mixture that it will turn more pinker, because we are adding more chlorocobaltate ions on the reactant, which means now we are favoring the forward reaction, né? So the answer here also always it will be more pinker. Sorry guys, this is fighting with me guys. I'm sorry. It will be more pinker guys, it will be more pinker. It will be more pink because of the when you add tetrachlorocobaltate ions, you are promoting the forward reaction to happen. So now we are on 6.1.3. What 6.1.3 asks us to do? So on 6.1, we are adding the concentration of hydrochloric acid. I said it before. Tetrachlorocobaltate ions. It is a blue solution, especially when you are reacting it with hydrochloric acid, which means now the solution it will be more blue because we are adding hydrochloric acid where on the reactant, which means now we are promoting the reverse reaction. So now we'll have more blue solution. Let's hope that our stream is still showing us. Yes, yeah, I'm glad now. I'm glad it's still showing us the right thing. Our technical issues guys are fighting with us. I'm sorry for that. I'm sorry. Yes, I hope now it's back. Our technical issues guys they don't want us, the material that I'm using, it doesn't want us to practice. I want you to practice guys. Final examination is the one that will determine your life from now on, if you be called a brother or a sister if you were doing grade 12. But if you didn't do well, you will be called by your name. But guys, let's got back to in business. We are on 6 point what now? Sorry for our disturbance. So now we are on 6.1.4. Okay, they give us the scenario also. The test tube containing the reaction mixture is being placed in a hot water bath. It is observed that the solution become more blue, which means now when you are increasing the temperature, okay, now go back to Lee Chatelier's principle. So Lee Chatelier's principle has its own factor that affect Kc, okay, or chemical equilibrium constants. Now Lee Chatelier's principle said that when we are increasing the temperature, you are favoring the forward or the endothermic reaction, the reaction that absorb more energy than releasing it, which means here when we are increasing the temperature, we are favoring endothermic, which means now because of the solution it become more blue, which means the reverse reaction is being favored, which means the reverse reaction is being favored, and the reverse reaction is endothermic, which means fourth reaction is exothermic, guys. So now the answer is exothermic, which means fourth reaction is exothermic because the increase in temperature, it is directly proportional to favorism of endothermic. I hope you guys you are following. So it is 1 marks. There is no reason they want to. It's exothermic, guys. Exothermic reaction. So now here they ask us why. Now we're going to tell them why we said that. It's because of we increase the temperature. The increase of the temperature, it is favoring the endothermic reaction will be, which is the reverse reaction. We increase the temperature. We increase the temperature. We increase the temperature. Which is favored the endothermic reaction, which will be a reverse reaction, which means which favored endothermic reaction. Favored endothermic reaction. Then equilibrium, it will shift to the left. So now our equilibrium it will shift to the left. It will shift to the left. So now this means exothermic reaction is forward. It means forward reaction is exothermic, which means exothermic is a forward, it's a forward reaction. Yeah, I hope we are done, guys. You go up with your 2 marks. Some of in some question it used to be 3 marks. You have to know these guys by your heart. If you don't know now, it's too late, guys, for you to know it. You should cram it, but I don't advise you to cram it. Okay, now we are going to 6.2. On chemistry, guys, the answer is on the scenario. You have to read the scenario. You have to reread the scenario if you don't know the answer. But in chemistry, you have to know that whenever you come across with the scenario, the answer is on the scenario. So let's read 6.2. 6.2 is read as follows. It's 3.01 times 10 to the power 23 molecules of N2O4 are sealed into a 4 decimeter cube container, which means it's a volume of the container, and then heated to a 400 kelvins. The following balanced equation represents the reaction that reach the chemical equilibrium in a container at 400 Kelvin. It's a temperature, get that, guys. It's a temperature. Then this is the following balance equation we are given. Okay, they also told us that at equilibrium it is found that 0.4 moles of N2O4 have decomposed, which means the thing that is being decomposed is being changed from its original state, which means N2O4 is gradually changing by 0.4 because at equilibrium, guys, you have to know that the number of moles on the reactants are not equal to the number of moles of the product, which means we start with the higher number of moles. The number of moles that we are starting with, we don't know yet, but we are given 3.01 times 10 to the power 23 molecule of N2O4, which means we know the number of moles of N2O4, but we have to calculate it, the number of moles that we are starting. But the number of moles of NO2, which are the product, it's 0 when we are starting the chemical in order to reach the chemical equilibrium. But first of all, they are 0. Here now, they ask us to calculate the equilibrium constant, which means we are going to, first of all, if they give us the number of molecule of N2O4, we have to use the quantities, the important quantities, the quantitative that we learned about them from grade 10. Those quantities say that number of moles is equal to its number of atom or number of molecules divided by Avogadro's constant. I think, guys, you all know this because it is a revision from grade 10. Guys, here we are going back from grade 10. The examiner like us to recall back. Now we have the number of molecules, which is 3.01 times 10 to the power 23 divided by Avogadro's constant. What is the number of Avogadro's constant? Because 1 mole is equal to 6.022 times 10 to the power 23 atoms or molecule. But here we're given molecules. Gap. This is mole. This is per mole. This is per mole, guys. So now the answer, it will be, let me take out my calculator, guys. Where is my calculator? Because I want to calculate it with you. I told you guys we should take out your calculator now. We're on the business to calculate. I'm sorry, guys. My stream is gone now. I have technical issues, guys. I'm sorry. So now I said before, we're going to use the important quantity that we've been taught about them on grade 12. Those quantities, it's where we said 1 moles of an compound is 1 mole is equal to 6.022 times 10 to the power 23 of atom or a molecule. But here we are given molecule, not atom. So we are going to use this equation in order to calculate the initial number of moles of N2O4, which will give us, when we calculate, it will give us 0.5 moles, which means now we have the number of moles, initial number of moles. So now we can come to our table, because now we also have the change of a number of moles when the chemical equilibrium was starting to happen. So now we come back to our reaction. We are using the rise table. Rise table, it will be like this. It's N2O4. Here is our reaction. It's 2NO2. Both of them are at gas phase. So now ice table, it will be initial number of moles, then change in concentration, then a number of moles at equilibrium, then a concentration at equilibrium. So concentration at equilibrium, guys. So now here is our table. So now, guys, we have here 0.5 number of moles, but when the equation when the reaction start, we have 0 number of moles on the product, guys, don't forget that. But we have to have minus, because now it's a change. This minus stands for a change in number of moles of N2O4, which will be 0.4. 0.4. If we didn't know the number of changes in number of moles of NO2, we were going to say X. Then the change in number of moles, it was going to be 2 times X, because we are changing by 2. It's one number of mole that produce 2 NO2, which means it will be 2X. So, but now we are given the change in number of moles, which is 0.4. So now we are no longer going to use X. Now we are going to multiply by 2. We are going to multiply by 2, which means it will be 0.4. Or you have to use guys, you should have been using the ratios. 1 is to 2, but we have 0.4 of N2O4. So now we have to calculate the change of NO2. It will be X. Then this one times this, it will be X is equal to 0.4 times 2, it will be 0.8. So now we have to write it as it is, guys. So here we have 0.8. In order to get the number of moles at equilibrium, we have to add this one, initial number of moles of N2O4 plus the change of number of moles. So we get 0.5 plus minus 0.4, then we get 0.4, 0.1 guys, sorry guys, 0.1. This is the number of modes at the equilibrium. This is the number of modes at the equilibrium, guys. This is the number of modes at the equilibrium. I hope guys you see it now. Sorry, our tablet is giving me problem today. It's because I'm not using my sorry guys. Yes, my tablet guys is giving me problems. Sorry. I'm so sorry guys. I'm so sorry guys. I am so sorry. I'm not happy too. And then in order to get this one, we will also add also on the product 0 plus 0.8, it will give us 0.8, which means we also have the number of moles at equilibrium. So now we're going to calculate the number of the concentration at equilibrium. We're using the number of moles. So the concentration equation is equal to number of moles over volume, which means we are going to say 0.1 over 4 is equal to 0.025. I think my calculator says so. 4. Yes, it will give you mole per dm cube. Mole, this one, mole the cube. So now it's mole per dm cube. Then we're going to write it on there, 0.25. Then this one, then 0.8 divided by 4, it would give us what? 0.2, because on this side we're going to say 0.8 divided by, because the equation sign is on that side, 4 is equal to 0.2 mole per dm cube. Here we go guys. So now we have the concentration at equilibrium. So now we can use the Kc equation constant. Kc, it says Kc is equal to a concentration of product divided by the concentration of a reactant. So the concentration of product is 0.2. Now you raise the coefficient of a reactant. So now the sorry guys. Deny. Sorry guys. Sorry guys. Let me try Sorry guys, as I was saying, now we're going to use the KC formula. To those who they don't know where does it come from, we're going to use the product concentration of a product with its coefficient. Here we'll have NO2, its coefficient, it will be the power now. Then here we'll have N2O4, its power, it's 1, which means we have the concentration of 0.2 to the power 2 over 0.025, the power 1. Then our answer, it will be, therefore our KC, it will be 1.6. So now guys, we are done. Thank you guys.